Today we're going to start by taking a look at some helpful takeaways about visible light and some of its characteristics. After that, we'll take a look at the relationship between the energy that an electron has versus the position that it has in the atom. Then we'll look at emission spectra of elements and how they are determined and how they help to refine our understanding of where the electrons are within the atom. And then finally, we'll look at the relationship between the different kinds of changes that electrons can make within the atom and how that corresponds to the light that we sometimes see emitted from different elements. So the calculations that you were asked to work on in the class notebook, you were asked to calculate the energy of a variety of different colors of visible light. Red was worked out for you entirely. That was the 2.72 times 10 to the negative 19th joules. And then we started working through the calculation for yellow. That answer was given in the class notebook page for you to do a self-check, as was the energy for green, which you can see in the right-hand column. The violet light, you did not have that answer for a self-check, so you see it here, 5.23 times 10 to the negative 19th joules. So I urge you to take a minute and check your calculations against these energies. Now the frequencies in the middle column there, you were not asked to calculate those specifically. And you may have if you did the two-step method to find the energy. But if you didn't, these would be the corresponding frequencies that went along with the given wavelengths in the problems and the energies that were calculated. And if we take a close look at those, realizing that all four of these forms of light that you did the calculations for are in the visible spectrum, that very thin section of the entire electromagnetic spectrum. Because they're so close together, relatively speaking, we would expect that there would be some similarities in some of their properties. And if we look carefully, we can see that all of their wavelengths are on the order of hundreds of nanometers. Well, remember, a nanometer is 10 to the negative 9th meters. And if we're going to put this into or express this in standard scientific notation form and in units of meters, this would equate to all of those wavelengths being on the 10 to the minus 7th meter range. So anytime you see an electromagnetic wave that has a wavelength in the 10 to the minus 7th meter range, you can assume that it's quite possibly, a color of visible light. If we look at frequency, notice that all of the powers of 10, the magnitudes of these frequencies are all 10 to the 14th power. And so we can make the conclusion that frequencies of visible light fall in this 10 to the 14th hertz range. Likewise, if we look at the energy, we see that consistently the energies are in the 10 to the negative 19th joules range. And so we can make the generalization that energies for visible lights will be in that 10 to the negative 19th joules range. Now realize there might be a little bit of variability if you're at the extremes of these magnitudes, like 1 times something or 9 times, the 10 to the negative 19th or 10 to the 14th, whichever value you're looking at. You may be slightly outside the visible range, but it's a pretty good bet that if you see those magnitudes, you know you're in the visible portion of the spectrum. Looking back and thinking back to the previous page that we had looked at, we looked at some comparisons between the relationships between wavelength and frequency, frequency and energy, wavelength and energy. And so if we take a look at the data that we see here, the color of light that's going to have the shortest wavelength is going to be the one with the smallest wavelength value, so that's going to be violet. And the color of light that has the longest wavelength is going to be your red light. If we think about frequency, and we look at the base numbers in the scientific notation there, we see that the lowest frequency, the smallest number, corresponds to the red light. And that should make sense, hopefully, because if you remember, wavelength and frequency are inversely proportional, so they behave in opposite directions. The highest frequency is going to be the one that you can fit the most waves into a given time period, so you would require a short wavelength, and so violet is going to be the color of visible light that has the highest frequency. Frequency and energy are directly proportional, so the lowest frequency light is also going to be the one that delivers the least amount of energy, so that would be your red light. And conversely, Your shortest wavelengths are going to be the ones that are the most frequent in a given time period and therefore deliver the most energy. And again, that would be your violet light. So if we think about electrons and protons, we know that opposite charges, opposites tend to attract. And so if we go back to our discussion of Coulombic attraction, as the negative electron gets closer to the positive nucleus, that attraction to the nucleus is going to get, see if you can fill in the blank here. As the electron gets closer, distance gets smaller. The smaller the distance, the greater the Coulombic attractive force. So the stronger the attraction would be. Now the next two questions here are talking about the energy possessed by the electron itself. Okay, that subatomic particle that's outside the nucleus. And both of these questions, they're kind of, reverse questions of each other. The first one is saying, for an electron to move from an energy level close to the nucleus to a level farther from the nucleus, the electron itself would need to gain or lose energy. And then if you look at the follow-up question, it's asking basically the same thing, except saying the electron is moving from an energy level further away to one that's closer. Would the electron need to gain or lose energy? So take a moment, ponder that, and have an idea of what you think it is. And then in a moment here, we'll resume and kind of draw upon some maybe prior knowledge from a prior discussion that you may have had in an earlier science class, but we'll try and make sense of exactly what's going to be true about the electron's energy. All right, so the way I like to think about the energy of an electron is an old demonstration I remember from junior high, middle school science. And it was in the context of talking about kinetic and potential energy. Now, kinetic energy is energy of motion, but potential energy is stored energy. It's energy due to position. And so if you think about a book sitting on a table, right, it has, in relation to the floor, a certain amount of stored potential energy because gravity is acting to pull the book down towards the floor. Right now it's being stopped by the table, but there's a certain amount of stored energy possessed by that book. Well, if I consider the book sitting on the table versus moving the book further away from the floor, say raising it up, now it's got more stored potential energy because the distance to the floor is greater. And so if we apply that line of thinking to the electron in the atom, in that first question, if I'm moving an electron from an energy level closer to the nucleus, the floor, to an energy level further from the nucleus, we had to put energy into that electron to lift it up, just as we needed to lift the book off the table. We had to put energy in to apply the force to lift the book. Okay? So energy from moving from an energy level electron, moving from an energy level close to the nucleus to a level further away is going to require the electron to gain energy. Another way to think of it is going back to the idea of attraction. Your electron is being attracted to the nucleus. Well, that force of attraction is holding it there. If you want to move the electron further away, it's got to overcome that attraction. So you have to apply energy in order for that electron to be able to move further away. So that's another way to think about the electron gaining energy as it moves further away. Conversely, if it's moving from an energy level further away, coming closer, it's going to lose energy. And it's in that loss of energy that we sometimes see light emitted from atoms. So one of the observations that was made in the early 20th century about different elements was that when they were energized, they would emit certain colors of light. And when that light was analyzed with a prism or a diffraction grating, it was found that those colors of light or that light that was coming from that source was actually made up of different colors of light, much like sunlight or white light from a light bulb diffracts to give you Roy G. Biv, the entire visible spectrum. So what you see here is a representation of an emission line spectra for hydrogen, and then you see one for boron underneath. So what I have here, I have kind of what's mocked up in the diagram there. But I have in the glass tube contains hydrogen gas, and it's in a high voltage source here. And so when I turn on the high voltage, all right, the electricity is going through that hydrogen gas and it's providing energy, and you see this purplish pink light that is being emitted. Well, if we were to take that light and pass it through a prism, examine it through a prism or a diffraction grating, we would see a pattern very similar to what you see there for hydrogen. And so that pinkish purple light that you see is not just one color. It's actually a combination of 4 colors: the violet, the blue green, and the red. And so that's unique to hydrogen. Any hydrogen from any source will provide that same pattern of wavelengths and also colors. If you look at boron, you'll notice that there are quite a few more lines. Yes, there's more electrons in boron, but that's not purely the determining factor. And like hydrogen, it's got a violet, it's got a blue-green, and it's got a red. But even though the colors are labeled the same, if you look at the wavelengths, they're not the same. It's a unique red, a unique blue-green, and a unique violet in each of those. And so the combination of the precise wavelengths of colors of light and the number of spectral lines that you see forms like a fingerprint for an element. And this is, quite frankly, what allows astronomers to be able to tell us the elemental makeup of a distant star that's literally millions of light years away, but yet we can tell what it's made up of. Not by sampling the material directly from that star, but by analyzing the light that has come through. And so Niels Bohr was a contemporary of Rutherford. So again, we're talking early-ish 20th century here. And he modified Rutherford's nuclear atom, the fact that the very small, dense, positively charged core in the nucleus, and the electrons were out there somewhere. Well, Bohr proposed a model where the electrons are actually in specific orbits that corresponded to different energy levels. And so when you provided energy to the atom in the form of electricity or maybe heating it up to very high temperatures, those electrons could move from their original or their lower energy state, and that was called the ground state, and they could move to a higher energy level, which was referred to as the excited state. And as the old adage goes, what goes up must come down. Eventually, those electrons, as you can see here in the diagram, the gray circle, eventually it's going to return to its ground state, and when it does, it's going to release that energy. Depending on the wavelength or the frequency of that energy, will determine the color that we might be able to see if it's in the visible spectrum. So if we look at these Bohr models, and when we talk about the Bohr model of an atom, sometimes it's called the planetary atomic model because it kind of looks like, the sun in the middle and the orbits of the planets. Not a perfect model, but that's just how it's referred. You see that, for one thing, the rings, the levels, are numbered. This is very much analogous to when we talked about Coulombic attraction, and we compared, say, lithium to sodium to potassium, and we said, hey, look, lithium's in row 2, and it's got 2 energy levels for its electrons. Sodium is in period 3, it's got 3 levels. Potassium's in row 4, it's got 4 levels. So these rings, these numbered rings, represent the energy levels where the electrons are residing. The other thing you'll notice is that there are 2 arrows in these diagrams. One is a straight arrow, and the other one's kind of a squiggly line. Well, electrons are particles, and particles move with a straight line motion. So the straight arrow represents the electron in its transition. Now, in the current models that you see here, it's starting at a level that is further away, and it is pointing towards and going to a level that is closer to the nucleus. So this would actually represent emission of energy or a release of energy, because remember, the further away the electrons are from the nucleus, the greater the energy is. The closer they are, the less energy. And so if we were to describe that transition, we do it by referencing the numbers of the levels. So for this first one, we would say n equals 6, 2 with an arrow, n equals 2. The squiggly line, represents the energy that is being emitted, and as you can see, there are some differences there with the wavelengths and the frequencies, and that can tell us something. But before we get to that, pause the video, and for models B, C, and D, fill in the electron transitions just like we did for Model A. All right, so hopefully, and you can check your answers against these, you got these transitions for models B, C, and D. Now the next part of the prompt, if you're following along in your class notebook, which hopefully you are, is to predict the colors that correspond to each of these emissions or these releases of energy. Well, at first glance, that might seem kind of hard because, well, Roy G. Biv, we got 7 colors there, but we also know that there's lots of different hues within them. So we've got a ton of choices for colors, but yet we're being asked for 4 specific colors to match each of these representations. And the key to getting those lies in the name of this model and what element we are referring to: hydrogen. Okay? Now realize, hydrogen's got a single electron, so all of these aren't happening at the same time for a single atom. When we looked at it in the spectrum tube, and you saw that light, there's literally millions of different hydrogen atoms, each one undergoing a different one of these transitions. And if we think about that emission spectra for hydrogen, remember there were 4 unique wavelengths, 4 unique colors: violet, blue-green, and red. Well, if we think about, okay, of these 4, which one's going to be the most energetic? Well, in A, okay, the transition was from n equals 6 to n equals 2. That was 4 levels. That was the most levels out of any of them. And they were all ending up at 2, so we can decide, okay, that's a representation of the greatest amount of energy. In the diagram, you can see the arrow is the longest. And all of these are drawn uniformly, so the longer the arrow, the greater the energy. If you look at the wavy line for the light that is being emitted, notice it's got the shortest wavelength, the highest frequency. Both of those point to the greatest amount of energy. So this first diagram in A is going to correspond to the color from hydrogen's emission spectra that is the most energetic. And of those 4, that would be violet. Probably the next easiest one would be go to the completely other end of the spectrum and say, all right, which of these diagrams represents the lowest energy? And that would correspond to the lowest color or lowest energy color of visible light, which is red. And so if we look at the rest of our diagrams, model D is going to be that lowest energy form of light. And so we would assign the color red to that one. So now that we've done those, that leaves 2 left and 2 models. So pause the video again and see if you can assign those 2 remaining colors to the proper models in B and C. All right, hopefully you had a chance to do that, and realizing that the next most energetic color is the blue-violet, and so you would want to assign that to the model that has the next shortest wavelength, and that would be B. So then that would leave C to be labeled as the blue-green. So because we knew what the emission spectra for hydrogen was and the specific colors that we're talking about, that's how we could assign these specific colors to these models. If we didn't have that, we can't just pull those colors out of thin air. We needed some additional information for that. So what we will be looking at next is working with models like these Bohr models and getting practice with drawing in the appropriate transitions for the electrons, the arrows for the electrons, identifying, well, what color of light do I think I would get for a particular transition, and we'll do that in class. One last note, in the class notebook, you'll notice that there's a couple of questions, a kind of a black and white diagram of line spectra, and a couple of questions. And what you've got there are the line spectra for 4 elements. Now, they're not in color, but you can at least see the position of the lines, which would represent the wavelengths of those. And remember, these are like fingerprints, okay? So you've got 4 elements that are identified, and then you have an unknown with its own series of spectral lines. And so the questions there are basically asking you, can you identify what elements are present in that sample and which of those 4 elements are not present in the sample? So give that one a try. We'll probably lead off with that at the beginning of class. But realize that your answers for those two questions are going to come from the 4 that are at the top of that diagram. So if you've got any questions, email me or send me a message in Teams. Thanks. Have a good night.